Okay, hi everyone, and welcome to the second of the 4 pre-kickoff seminars. As you know, we're intending to do one of these each week until the kickoff meeting with a different science focus each week. Last week, we heard from Michael Coughlin about the MMA stuff. And this week, I believe we're hearing from Mia and HEP.
Yep.
Right. So if you'd like to take it away, Mia, thank you.
Okay. Can you see the slides?
Yes. Great. Thank you.
Okay. I'll get started. So I'll talk about the E33 HAP activities. Specifically, how do we want to improve the discovery potentials with the artificial intelligence at the LHC? So, just in case you're not working on particle physics, we actually do something that's pretty crazy, that we try to recreate the universe right after the Big Bang. That's, 10 to the minus 10 second. So we can see how things evolved since then. For such a crazy project, right, we have a very good model that could describe many things we observe in the collider experiments we built on Earth. And to summarize, how many particles have we discovered and how do they interact with each other? We have the standard model of fundamental particles, where you know exactly how many particles you expect and how do they interact with each other. And everything is summarized very beautifully in a mathematical formulation that you can do calculations with the quantum field theory. So it has been pretty successful. And in fact, the last missing piece of the standard model was the Higgs boson, and was discovered in 2012 at the Large Hadron Collider located at CERN, Switzerland. So it's this 27-kilometer accelerator ring where we accelerate proton beams and collide them at different experimental sites. Then we built these huge detectors underground, about 100 meters underground, to try to see what comes out of the collisions. For example, the Higgs boson was discovered jointly by ATLAS and CMS experiments, where the specific design of these giant machines are different, but the detection experimental technology are comparable between these two. So just as an example to show you how we found the Higgs boson is by detecting these particles that come out of the collision. So for example, the Higgs boson decays to other particles, and the type of particles we can detect are these few as shown in this slide. So in the inner part, this is kind of the cross section of our detector, and the very inner part is the charged particle tracker, and these are used to detect the charged particle trajectories because they bend in the magnetic field that's produced by this superconducting solenoid. So in MS, we have a 4 Tesla magnetic field. So something that's charged, such as electrons, or charged hadrons, such as pions, they would curve in the magnetic field, and we can reconstruct the momentum and kinematics of these particles. And after that, there's the calorimeter. So I have the electromagnetic calorimeter and also hadronic calorimeter. So for example, things that interact only electromagnetically, such as electrons or photons, would deposit most of the energy in the electromagnetic calorimeter. So from this energy deposit, we can measure how much energy these particles are carrying. And for these hadrons that interact strongly with the hadronic calorimeter, we can also measure the energy of these particles. And for muons, they interact minimally with the detector, and they are detected by the inner tracker and also the muon chambers that's outside of the solenoid in SEMAS. So for ATLAS, it's slightly different, but the ideas are very similar. And to discover the Higgs boson, we actually discover, what comes out of the Higgs boson decay. So we produce the Higgs boson in the proton-proton collision. And the Higgs boson decay, it can go through different modes. And the channels we rely on for the discovery was actually the more clean, although rare processes. For example, in this event display is showing the Atlas detector, where you have the Higgs boson produced, and it decays to 2 Z bosons, which are also very heavy. So these decay right away. What eventually you see in the detector are actually these muons and electrons that's detected. Then you can measure the properties of these particles and try to reconstruct what happened in the collision in order to find the Higgs boson. So as I mentioned, these are actually rather rare decay modes of the Higgs boson. For example, only less than 3% of the Higgs boson decays to ZZ. A large part of the Higgs boson decay, that's to BB bar, that's 60%. Actually, it's even more challenging to measure for several reasons. The first is that we have much larger overwhelming background, so up to the 10 to the 7th more frequent background for Higgs to BB decay. This Higgs decays to B hadrons, which are long-lived, so they can travel a little bit in your detector. So it's a bit more complex than, for example, electrons and muons we detect. All of these things, contribute and make these Higgs to BB detection almost impossible. So that's where, where we started exploring more like machine learning based techniques, multivariate techniques, starting from BDT and more neural networks. So for example, here, so you have a Higgs decays to BB bar B hadrons, and they travel a little bit. So you have a displaced vertex and displaced tracks. And the decay products coming from this B hadrons are also tend to be very soft. So only with the machine learning techniques, multivariate techniques, we can do rather good discrimination of this Higgs to BB classification against, for example, a background event. So on the right side, in this plot is showing the ROC curve of how well we can detect the Higgs to BB decay. So this blue curve is a boosted decision tree based method that use more derived expert features as inputs. For example, if the particles decays from here and also the secondary vertices. So we were able to improve, how well we can detect the Higgs to BB decay with more advanced techniques, neural networks, for example, recurrent neural networks and convolutional neural networks. And more recently, there's a large improvement brought from using this graph neural networks, which I will get into more details later on this application. But basically, you can build a graph using the particles from the B hadron decay and also the secondary vertices, and build the inhomogeneous graph and try to identify these Higgs to BB decays. So this is kind of, to show you how where we can get machine learning to help us with our physics goals. And of course, we have good reasons to believe that the standard model is incomplete. To some, at some energy level, we don't know. So theoretically, we know that we have a 125 GeV Higgs boson that in theory, it would receive the loop contributions from the standard model particles based on quantum field theory. So if you take all the physics valid to Planck scale, that's the energy scale where Big Bang happens, then there's this absolute number that needs to be really finely, carefully tuned in order to make this 125 GeV Higgs boson. So we often refer this to, as the unstable Higgs mass or fine-tuning problem. But for the Higgs field itself, we don't really know why it's the way it is. At the beginning of the universe, you have a more parabolic type of shape. And then at some point, this phase transition happens and all the particles acquire mass, but we don't know the dynamical region of this. And of course, experimentally, the standard model is not complete because we don't include the dark matter energy candidates, which convincingly from cosmological observations, we know there's dark matter and dark energy. And also we don't know about the origin of neutrino masses, which we know neutrinos are massive because they oscillate. And there are a couple more, experimental anomalies in the charged lepton sectors that tend to indicate, maybe the lepton flavor violation university is violated. And there are beyond the standard model theories, which can give good explanations and also solutions to many of the problems, or include some of the experimental anomalies, or try to address those in one theory. So, for example, supersymmetry was very popular because it solves the problem of stabilizing the Higgs boson mass by canceling the top loop contribution with this scalar top partners. And also, it has a dark matter candidate that comes for free. That's the most stable long-lived particle in SUSY. But we were able to perform and search for these particles really extensively, and we were able to study a large parameter space in theory that was not possible with the LHC data set. And here's just a few plots to show you how far we've made, right? For the stop pair production, for example, we were able to push things more towards like TeV scale. So everything inside this loop will be excluded for the theoretical phase space we're studying. And we were also able to study more rare processes in the electroweak sector of the supersymmetry particles, which is less often that happens in our collider, but also theoretically as valid to solve some of the problems I mentioned. We also have very extensive dark matter searches, but we're very good at placing limits. So the question is, are we doing the best we can? If you zoom out a little bit to look at the theory parameter space, we look at the LHC, we are actually quite constrained because of how we designed our detectors to be sensitive to searching for the Higgs, for example, and SUSY particles, which tend to be what we call prompt signatures that tend to decay in the beam pipe once it's produced. And all of these tend to have relatively high energy. So we kind of constrain our search space in this box that if the new particle, the BSM particle beyond the standard model particle, is either low mass or weakly coupling, then we lose sensitivity of searching for these particles. So the general direction of where we're going at the LHC is to look for this very low mass and very weakly coupling particles, and that's very challenging for our detector to detect and analyze. Some of these would resolve in some unconventional, we call signatures, which tend to live a bit longer than the normal signatures we look for and decay in the detector instead of inside where the proton-proton beam collide and happens. So many of these are limited by the online data collection of our experiments, simply because we didn't build the LHC to look for this type of events. And currently we would rely on something, accidentally you would have another object that you would trigger on to study these signatures. So this is something we can improve in the future. And also going towards the higher energy regime. So the LHC has the highest energy proton-proton collision. And there are several things we can do to improve our sensitivity of studying new physics that's more like at the energy level we can reach with the experimental condition. So one example I showed is to improve our detection for this very energetic high PT objects, for example, the Higgs-2 BB decay. And also you can go another route if the new physics is really like orders of magnitude beyond what we can do at the LHC. Some of these would come in loop contributions, and you can calculate the correction of these really heavy particles, and they would modify some of the rates of very rare processes. So one example is a lepton flavor violating process. And interestingly, for these signatures, some of them would produce rather soft, low PT, signatures that we are also, not very sensitive to the LHC, like how we designed it to be. So I kind of, discuss how we can improve some of these directions with machine learning. Another side of the story is more like the very challenging experimental condition at the LHC. So we have proton-proton collisions at every 25 nanosecond. The LHC is very good at increasing the amount of collisions they deliver by packing as many protons as possible in each beam crossing. So to increase the probability of these protons colliding. So which means you can have multiple protons colliding in each beam crossing. So this is good for increasing the luminosity, which means we have more statistics to study our theories that new physics we're looking for. But it also is very challenging experimentally because essentially you're only interested in one interaction that happens in this per bunch crossing, and then you have other ones that also produces particles, but these are considered noise that you need to subtract from. And from a detector point of view, that's only from the production point of view, how many Higgs bosons you can produce, for example, how much data rate you're dealing with. From the detector point of view, it's kind of like you're trying to find, some anomalous raindrops from rainfall, right? Like when you have like lighter rain and heavier rain, of course, with heavier rain, you have larger statistics to work with, but then you need faster cameras, which means you want faster shutter speed and probably higher resolution pictures that you take in order to really resolve what happened in this event. So often we found ourselves in building faster detector electronics detectors and also with finer granularity, so have more readout channels in order to collect enough information that comes out of the collision to reconstruct what happened, whether there's new physics inside. And often we found that machine learning can help us with improving many aspects of this. So another, story is that we found ourselves using more and more, even more graph neural networks, simply because I think it's a very natural representation of the data we collect in our detector from raw detector inputs level to reconstructed particles. You can imagine that you can represent a charged particle leaving like hits in the tracker, and you can represent each of these hits as a node, and you can connect these nodes with edges and try to build the whole charged particle trajectory. So, and also when you have reconstructed particles, you can represent these particles as a node and how they interact with each other as edges. So graph neural networks has a formulation that helps us to represent this irregular and structural data, and also has a way to explore the relations between these nodes, so our measurements or particles. So graph neural networks, a lot of these, mathematical formulas was driven by social media data and how to adapt to our domain knowledge that we perhaps know there's some embedded symmetry or structure that we can take advantage of, or to embed this domain knowledge would be interesting to explore. And how to formulate the problem depending on the target you're trying to hit is also interesting. So in general, there are like several categories we can classify the GNN applications in particle physics. And so we have the node classification, graph, edge, where you can try to identify subgraphs that belongs to the whole set. So I have a few examples which yes, by definition biased. So most of these are work by, done by the E3D3 members, but hopefully I can give you I can illustrate the general idea about how to formulate a particle physics detection question as a graph neural network problem, and how to solve those problems. So as I mentioned, Pileup is kind of a general problem challenge for all kinds of particle physics analysis these days, not only the unconventional ones, but also if we detect a particle, we want to know how much noise is contributing to that. So this is kind of the situation we're dealing with. We have 100 proton-proton collisions, and we only use one of these as the interaction of interest to do physics analysis of. Of course, it's obvious that it's essential to the LHC physics program overall, because we need to understand when we reconstruct a particle, how many constituents of this particle are actually coming from noise interactions, from Pileup interaction, and be able to remove these. And to do this, we have two classes of particles. So we have the charged particles and neutral particles. So charged particles will bend in the tracker, and since we have very excellent detection in the tracking system, we're able to take the trajectories of these particles and reconstruct and distinguish the Pileup interaction, where they come from the primary vertex that we're interested in studying. So these are easy, but what's tricky is the neutral particles, that we don't have the tracking information to associate them with which interaction point they come from. So often you have to rely on some transferred features to subtract this energy of the neutral particles in order to do this. So as an example of a node classification for graph neural networks, we did a study to apply this graph neural networks with the semi-supervised setting. So basically, the setting is that the association of the charged particles to the primary vertex and also Pileup vertex. For the charged particles, you can train a feature extractor or classifier with graph neural networks that learns about the surrounding environment of this particle that can be transferred to neutral particles. So when you train this, of course, you don't want to use the charge specific features. So we remove those from this training. But once you learn this classifier about this surrounding environment of the charged particles, you can apply this to the neutral particles and try to label the neutral particle as interesting from the primary vertex or from Pileup vertex. So we did a study of this, and it outperforms the expert feature-based method, which is a similar idea, but you extract the surrounding information from domain knowledge-based feature extraction. And this is also comparable to a fully supervised method. So it's easier to see perhaps in this ROC curve, where better is like top left direction. And you can see from the log scale better how the graph neural network based methods outperforms the red one, which is the expert feature-based method. And this green and blue line represents the separate semi-supervised, where you learn from charged applied to neutral, and fully supervised, meaning you know about the neutral particle labels just to see whether you have performance degradation from a fully supervised setting to semi-supervised setting. And the performance drop is quite negligible. So we presented this in conferences, and there's papers coming soon. So this is in collaboration with Pan, who's also part of the A3D3 community. So we are interested in applying this to CMS simulation and real data. Moving forward, perhaps we can address some of the more challenging scenarios where in the forward detector region, we don't have neutral particle vertex association. How do we do this Pileup subtraction? And perhaps looking into if we have the association of these Pileup particles to which vertex it belongs to, including neutrals and charged particles, can we do physics with these Pileup interactions? Okay, so that was a case for more like node classification application of graph neural networks. As I mentioned, we can also do graph level classification. The Higgs 2BB tagger is kind of an example of those. But here I'll show you also an ongoing study in collaboration with Pan at Purdue, trying to detect some of the very soft, very challenging signatures at the in CMS. So this is, we call tau 2,3 mu. So tau is the third generation lepton, and muon's the second generation. And if we believe there's a lepton flavor universality, this tau 2,3 mu event would never happen at tree level. They can only happen with loops that violates the that's through neutrino oscillations, as shown in this plot in this diagram on the left here. So since they're like loop contributions, they're like super rare in the Sena model. So it's 10 to the minus 14 branching fraction. If you have a new physics that comes at tree level, for example, from R parity violating SUSY, this process would have enhanced production to the order of 10 to the minus 8. So, but these things are really difficult to detect in CMS because specifically for tau 2,3 mu, we have the d mesons that decays to tau that decays to 3 muons, and that's the main source of taus we use. And since the d meson and tau are very close in mass, so these 3 muons that come from this decay are very collimated, very soft, and tend to populate in the end cap of our detector. So traditionally, we don't really optimize for this type of detection. And for the next upgrade of CMS, we actually uses the information with better resolution from the tracking systems. But even with that, we can only detect 25% of the decays. So on the right side, you can sort of see where this, so this is the muon PT spectrum for this tau 2,3 mu events. For the 3 muons, the blue one's the leading PT muon, and as we go down, goes softer. And just as a comparison for the online filtering for the triggers we have now for single muon, dimuon triggers, we are more like 20 GeV, 10 to 20 GeV. So you really need specialized triggers to detect this type of particles or processes. So we are working on this graph neural network based, whole graph classification that takes the muon hits that includes the coordinates of these hits from the measurement in your muon chamber and represent this as nodes in a graph. We have an attention-based graph neural network to aggregate information between hits from different layers and from different measurements, and also there's a global node to aggregate this information. And then you can do a classifier training signal mixed with your background noise coming from Pileup and versus pure noise coming from Pileup. And we were able to do like 90% efficient. And this is, some number you can compare to this 25% efficient. So we are, excited about this. But this is kind of an end-to-end approach where we know there's a tau 3 mu with what probability, but to reconstruct the full kinematics, you probably want to take, for example, shown here, is the eta versus phi plane of the hits coming from different stations of the muon chamber. And you want to be able to take this information and reconstruct what really happened in the event. So for example, if we're lucky to see some enhancement in some in this process, and then you want to be able to know what's the properties of these particles that end up having producing these hits in your detector, and try to trace what new physics it could be. So that involves some regression and such. And I'm also interested in studying how we can adapt this type of neural networks to other type of physics signatures, for example, long-lived ones or outside of CMS, and to test how adaptive machine learning methods can be. Okay, so that's more like an end-to-end, given raw detector inputs, and you get an answer of whether this is interesting or not. But in reality, traditionally, how we do physics at the LHC is more like staged reconstruction. So first you have the tracking information detected by your tracker left by charged particles, and try to connect the dots to reconstruct the charged particle trajectories with the measurement of the, the momentum and the bending, all these things. And in the electromagnetic calorimeter, you try to find clusters of deposits of energy, and you collect all this information, try to, combine them, link them, and to come up with, whether this is a muon or charged hadron or photon or neutral hadron based on the characteristics and of, combinations you can make. And this is called the particle flow reconstruction in SMS. And after that, you take these reconstructed particles and try to reconstruct what physics process actually happened in this collision. So today, I'll show some studies that our A3D3 members are doing in the tracking and also particle fluid reconstruction. So this is not very the most inclusive, but just to give you some ideas of where we can apply these graph neural networks. So for particle tracking, as I mentioned, you basically take the measurements that's left by these charged particles in the tracking devices. So we have layers of this. And you would have hits, and then after this layer, there's some spatial separation, and you have the second hit. So the task here would be to identify between layers and across layers, which connection is the right connection. So often we formulate this problem as an edge classification question. So, and the reason for using machine learning it's actually mostly motivated by speeding up the algorithms, because traditionally we use like a common filter based method that goes outside of the detector and goes back in. It actually works pretty well from accuracy point of view, but it's very computationally expensive, and it's by nature a sequential algorithm. So we can't really easily take advantage of this coprocessors, for example, heterogeneous computing like GPU coprocessors in order to speed up these algorithms. So you have to do some smart tricks in order to do that. And the idea of applying machine learning is that, often the computation neural networks are parallelizable by definition. So we want to see if we can do efficient tracking with machine learning. So in this slide, I'm showing some examples, also studies done by our A3D3 members for accelerating tracking reconstruction. So very specifically, this is targeting very resource constrained scenarios on FPGAs. And we were able to demonstrate, for a graph that has 112 nodes and 148 edges. If you go to like a 12 bits precision, you can achieve quite high precision. And also this one is showing some of the timing performance in terms of latency. So it's so this is in terms of cycles. If you do like 170 times 5, that's less than 1 microsecond for this graph, for this edge inference. So we were able to, implement a GAN on FPGAs that does particle tracking that's quite efficient. But this is targeting kind of small applications. Okay, so this is the first step of the reconstruction at the LHC, where you build tracks and clusters. Another example is how to take these tracks and clusters and combine them and reconstruct the particles that actually were detected. So here I'm showing an example of this particle flow with machine learning. So basically the problem you're trying to solve is to take these clusters. So for example, this plot is showing these blue ones are from electromagnetic calorimeter clusters, and the orange ones are the hadronic calorimeter clusters. You want to take all these clusters and try to see whether you can combine these with the tracks that's showing in gray here, and come with another set that's representing your particles. So basically, from like a machine learning language, we're trying to do a set to set translation. Of course, we want to combine this set to, in a meaningful way, so we can have the regressed particle properties to match what we expect in our generator level, which means we know what the true particle should look like. And this graph neural network-based approach tend to, it was shown to perform really well based on Adolphi's data set. So this left plot is showing the classification performance. So basically, if you have a muon, how often do you reconstruct the muon as a real muon? So ideally, you want things to be a diagonal, but of course, there's limitations of how well we can separate electrons and gamma, for example. So we have some confusion here. And then for, to reconstruct the properties of the particles, you want to learn about the momentum. You want to learn about which direction it's traveling to. So this here on the right side is showing the regressed value by the graph neural network compared to the real value. And this is also compared with the rule-based, which is the blue one. So overall, the machine learning-based method performs the same or even better with than the rule-based particle flow algorithm, which is encouraging. So the previous examples I showed you kind of, it really helps to improve a lot of discovery potentials, given that you know where you're looking for. This slide is showing another way we're going in our searches, which is what if we don't know where we're looking for this signal? So we don't know what to design to improve the detection efficiency, to improve, maximize that. So basically you can build this autoencoders that learns a representation of your standard model particles based on the distributions you gave it, and try to identify and treat this as more like an anomaly detection problem in case you don't know where the new physics might pop up. Okay, so all the above ones are more like, I hope that the problem formulation and motivation was clear. In reality, a lot of these algorithms, we need to either apply them in the online filtering, so we have better signal acceptance that fits the bandwidth we can read out from. And also for offline computing, you want something that's efficient and fast enough so we can fit the computation within the resources we have. So the question is how we can be fast enough. And of course, fast enough is up to your interpretation, and really depends on which system you're working with and what metric would be most important for your problem. At the LHC, we kind of have a spectrum of different data processing requirements. So we have proton-proton collision at 40 megahertz. So every 25 nanosecond, we have collisions. We have billions of channels that read out detectors with many bits that we cannot really read out everything off. So only part of the information is passed to we call level 1 trigger. So it's the FPGA-based trigger system in CMS, for example, where a quick decision has to be made about whether this is interesting or not within the time budget, about 1 microsecond. Because the raw information is sitting on detector on the electronics, and you only have so much buffer. So after this level 1 trigger processing filtering, we reduce the rate to 100 kilohertz, where it gets further reduced down to 1 kilohertz, where we have a high level trigger system that's based on like a CPU farm. So you can have a bit more time storage for your input data to make a better decision about whether this is interesting or not. And what comes out of HLT gets sent to offline data processing where it's distributed around the world. You might want to do multiple processings. You might want to do multiple track reconstruction, for example. So for the level 1, the main concern or restriction that's more strict than a lot of systems is the latency. So you need to make a decision in 1 microsecond level, and you have several applications coming from different parts of the detector, which means that each of these algorithms tend to consume about 100 nanosecond, or not much more. So this is very targeted systems in the A33 language, right, where you have high bandwidth, very low latency processing using specialized computing hardwares. And for the HLT and offline computing, where it's traditionally CPUs, multi-threaded computing, but we're moving towards more increasingly heterogeneous systems, for example, by including GPUs in our HLT or offline computing. And in the fast machine learning community, we have been pursuing solutions for both of these areas of applications. For the FPGA implementations that's targeting specialized systems, we have this HLS4ML project, which you probably heard something about, but I think we'll hear more about this in the future, which it stands for high-level synthesis for machine learning. Basically, when we try to think about how do we program these neural networks on FPGAs for our trigger applications, there was a missing link between the machine learning world and how to program FPGAs, especially for domain experts who might not have the knowledge of programming FPGAs, or both knowledge of developing a neural network and also program FPGAs. So this has been a very active and successful effort, and we have multiple applications in CMS that are being deployed using HLS4ML. For example, we have the Miaoyuan PT regression in NCAP, where it's based on a fully connected network, and we have other triggers being deployed, including some of the anomaly detection ones I mentioned. And for the HLT and offline computing world, the challenges are a bit different. Here you are more relaxed in the latency. Actually, a CPU, multiple thread based CPU plus a GPU attached to a local machine sometimes will work. So here the challenge is more like these hardwares are more they're expensive, and often how you set up the computing paradigm determines, right, how cost effective your solution is. For example, buying individual GPUs for all the CPU nodes, perhaps depending on your application, is not the most cost effective way. And you also have a dependence on the hardware you purchase and decide to use. So we kind of explore a machine learning as a service. We call this Sonic project, where we are exploring a more cost-effective, where you can saturate your GPU usage, for example, that provides more flexibility. We can do GPU coprocessors. We can work with FPGA coprocessors, and also more scalable. And also, plus bonus is that it's a pain to include these machine learning packages in software stacks, such as CMS software stack. So it also reduces the software maintenance because you offload this to the server side. So we are also, pursuing applications in CMS data processing in multiple workflows for both machine learning and non-machine learning CUDA code. That's for HLT. Okay, so here's my summary. So I hope I convinced you that machine learning offers opportunities to help us to discover new physics at the HC. And to do this, often we need accelerated machine learning inference in either online processing or offline processing. And many of these implementations would require a multidisciplinary team to realize the optimal implementation. for both targeted systems and heterogeneous computing systems. And we really need user-friendly tool for domain experts in order to streamline the process from ideas to implementation. My discussion today is perhaps a bit biased towards like what I do now and what people do in E3D3 for the HEP community. So there's a lot of graph neural networks and mostly focus on reconstruction. But there's also other areas that we can explore in the future. For example, how to speed up simulation, which is also relevant for our computing. And also, online experimental control and calibration, which is also, could benefit from the real-time inference of machine learning methods. So I look forward to working with people in the E3D3 and in particular, whether we can identify synergies in machine learning method development based on the commonality and synergies of our applications and problems we're trying to tackle, and also advance, our machine learning methods implemented on targeted and heterogeneous computing systems with the engineering and computer science experts, for example. That's what I have for today.
Thank you very much, Mia. That was a great overview of, well, as an astronomer, I found this was a great overview of HEP and what's going on. So very informative. Questions, please, from anyone. Either on chat or raise your hand. Phil.
Hi, yeah, sorry, it's a bit of a physics question for Mia. For the tau streaming analysis, I'm wondering, were you thinking about using this in a scouting system?
I think it's possible, but even without scouting, you can do this with the 90% efficiency. So it wouldn't improve things much.
With the 20 GeV muon PT trigger? So,
oh, I don't know if you can like trigger these events in the 20 GeV one.
Yeah, that's my point, is that the trigger level, I'm pretty sure like the trigger level, I don't know how you would get these, right?
Yeah, so this is what I'm saying. This is not the scouting. This is the nominal trigger system. Yeah, that you can just pass things through and it would fit how much you can read out in the normal muon trigger system.
I see. And this passes, like, have you run the signal at like 200 Pileup? It passes like the trigger?
You mean the single muon trigger?
Or the dimuon?
Or the dimuon? We haven't tested that.
Yeah, because like naively, I would have expected this to be, I mean, I agree that like with, normal Pileup, it's probably doable, but like, at very high Pileup, it might be a challenge to get like.
So
good.
this, right. Yeah. So this 90%, so this is actually 200 Pileup.
Okay.
So we measured the trigger event with the 200 Pileup sample.
I see. Okay, so you've done the trigger studies. Okay.
Yeah.
All right. Well, I was hoping this would be a fun scouting example, but if it's already triggerable, then it's fine. So.
I mean,
yeah.
You can see, I think to me more like this project where it's going is, yes, you can trigger on these events, but can you actually reconstruct the event? It's a bit
No. I think it's a great study, right? And it's a great analysis. And yeah, there's a huge ambiguity here for how you want to reconstruct these. I was just, so let me explain to everybody is that scouting, what that is basically real-time, what we call real-time analysis of the data. Some people call it trigger level analysis. And so the idea is that you take data and you do the analysis simultaneously. The only reason I ask here is that as an application of A3D3 scouting is like scouting analyses are like great examples because you have to run them fast. And because basically the idea is that you don't save these events and later on downstream because they just look like most of them are garbage. And so you want to basically do the processing in real time. I thought these might be scouting events,
I mean,
but yeah, it's fine. I mean, I still think it's an interesting problem, right?
I think it's definitely possible, right? Especially if we don't want to go through the process of adding a trigger line for this specific application or replace what's in there now, right? There are bits of things you have to compete for. So I think scouting will be interesting, yeah, from that implementation consideration.
Yeah, but I mean, this is a great like example anyway, because it's an interesting problem.
Yeah. Yeah, we can talk more offline too.
Okay, any other questions for Mia? Well, if not, people are, of course, free to continue discussion on Slack and all the other channels that we are now getting for communication. So thanks again, Mia. I believe next week is Amy Osborne and neuroscience. So same time. Otherwise, everyone have a good week and thank you very much.
Thank you. Bye.
Thanks. Bye.